Well, thanks folks for coming, those of you who are over Zoom as well. So today we are very grateful to host Itai Lang. Itai is a postdoc at the University of Chicago, working with Rana Hanukkah. Before that was a PhD student at Tel Aviv University. And he's been doing some interesting work with the intersection of geometry and machine learning, particularly on some of these techniques for how to leverage these emerging vision language foundation models to do 3D shape analysis and editing tasks. So I think today we're going to hear about some of the cutting edge stuff that he's been up to. So take it away, Ethan.
Thank you, Daniel. Thank you so much for the introduction. Let's see if this thing works. Oh, it works. Amazing. Okay, thank you, Daniel, for the kind introduction. I must start with a personal note. About a year and a half ago, I met with Daniel and Adi regarding a project that we've discussed, and they brought a possibility for coming and present at the Brown Vision Computing Seminar, but unfortunately, it didn't work out back then. But luckily, I met Adi at the last SIG of Asia conference, and we've discussed this subject again, and I'm so excited that it is happening, and I'm very happy to be here today. So today I'll be talking about clicks and prompts, intuitive methods for geometry processing, including click-based interactive segmentation and text-driven local editing of 3D shapes. Daniel introduced me, so I'm a postdoc at the University of Chicago, working with Professor Rana Hanukkah and enjoying it very much. I did my PhD study at Tel Aviv University, where I was advised by Professor Shai Avidan, and I also interned at Google Research, where I worked with Niki Rubinstein. Okay, so I'm very excited about 3D data. And 3D data and digital content is everywhere and relates to many fields of life. It is used in manufacturing, engineering, virtual and augmented reality, medicine, and entertainment. And thus, the demand for tools that can process and edit 3D data is immense and increasingly growing. But the current tools that we have are largely inaccessible. For once, they required significant time and experience to operate them, and I can tell you that from experience. And even after you invested this time on learning how to operate these tools, still the process of creating and manipulating 3D data is very tedious and requires a lot of effort. And this situation is a bit more complicated than we would want it to be. So we definitely need simpler and more intuitive solutions to interact with 3D data, and a possible solution is clicks. And why is click such a good interface? Because it is intuitive. We click on things every day. I mean, I click on my phone 100 times a day. And a good thing about clicks is that they are specific about the where. Let's say I want to interact with some region of the shape. I can click on it in order to convey my intention regarding that. Another possible solution is text. And why text is such a good medium? Because similar to clicks, it is intuitive. Let's say I want to do an edit of a 3D shape, so I can describe my edit with words, which is quite straightforward. And another good thing about text is that it can be precise to some extent about the what. I can describe my edit with several words, and this is quite simple and straightforward. So this is what I'm passionate about. I'm passionate about working, about creating creative tools for innovative problems in geometry processing, like interactive segmentation, local editing of 3D shapes, and recently we've been working on geometric stylization and much more. Okay. Great. And as part of my work, I'm working on harnessing, like Daniel mentioned, the great power and potential of recent deep learning techniques. But although they're amazing advances, the amazing advances made by deep learning techniques, they require a lot of data, a large amounts of data. And as we've discussed before, it is not that easy to create diverse and high quality 3D data with intricate geometry and expressive textures. So training models with 3D data is quite challenging. Okay, and as we know, 3D data sets are relatively scarce. On the other hand, creating diverse and high quality 2D data is very easy. Nowadays, we can take our phone, snap a picture, and it would be very good. And there are currently large-scale, massive data sets of 2D data of high-quality images and diverse spirits. And consequently, nowadays we have powerful 2D foundation models trained on these massive data sets. For example, this is a text-to-image diffusion model, latent diffusion, that generated the image according to the text prompt, an astronaut riding a horse, and it was trained on a dataset containing 5 billion pairs of images and text prompt describing them. And as you can see, this image is of high quality. We have a lot of details on the astronaut and the horse, and it conforms pretty well to the text prompt. And the emerging question is, how can we bridge the gap between these 2D worlds, the 3D world and the 2D world? But by the way, are we doing questions during the lecture or the end? I mean, it works either.
However you like.
So okay, if anyone wants to ask a question, go for it. Yeah, I'm fine with it. No problem. Okay. Yeah. And an answer, the glue between these 2D worlds, this 3D and 2D world, is rendering, which means projecting the 3D geometry into 2D images. And although we lose some information in the process, images can still provide natural cues for geometry understanding. And this is actually the way that we perceive the world. Think, for example, about this image. If we see this cylinder from a single view, we can imagine how it would look in 3D. So they provide sufficient information for geometric understanding. And fundamentally, now that we've projected the 3D geometry into a 2D image, we can now leverage these powerful pre-trained 2D models trained on these large, massive 2D data sets for learning in 3D. And although we do not have large-scale 3D data sets, this is less of a problem now because we can use these powerful 2D ones. Okay. How does this pipeline usually work? What we want to do, we want to optimize a 3D representation using the supervision of a 2D model. Here in this example, we have an input 3D shape, and we want to do some 3D operation on this shape, in this case, texture the shape. And what we do, we use a differentiable renderer to project this image into 2D. So now we have a 2D image of the 3D model. And now we can use this 2D image with a pre-trained model and apply our laws in 2D. In this example, we want to align the texture of the shape with the text prompt adorned with sprinkles, and we can use the relevant 2D model for that, apply the loss in 2D, and now since we use differentiable renderer, we can propagate our gradients from the loss through the differentiable renderer to our 3D representation. Okay, now that we've covered some background, let's start talking about the first topic, which is click-based interactive segmentation of 3D shapes. And this is a work that we've published at the last SIG of Asia conference where I met Adam. Okay, what our method do? What we do is click-based interactive segmentation of 3D shapes. Let's say that I want to get this box region of this alien shape. With our method, what we do, we click on that region, and our method predicts the region that corresponds to our clicks. Now, the method is interactive, so if you want only the extruded part and at the front of this shape, we can add another click, a negative click in this example, which means that we want to exclude some region, and then it excludes the region and give us the region that matches this combination of clicks. Now, interactive segmentation in 3D is a very challenging problem. And for starters, we do not have a dataset with annotations of 3D shapes and clicks that tells us what is the corresponding segmentation according to the clicks. What did previous method do? Previous method worked either worked on a specific shape domain. Here you can see the human body. And even if the data set contains shape instances of different types, for example, furniture and vehicle, still the set of possible parts is predefined in advance and fixed. And in our case, we are not limited to any shape domain nor to specific predefined parts. Our method is called ISEG, is optimized to the shape to capture its unique and specific regions.
So ISEG is the new one.
Yeah, ISEG is the.
When we say optimized to a specific shape,
So.
or this we'll see in a second.
Yeah, we will see.
Great.
What it means is that this method, our method captures the unique regions of a shape. Let's say that you have a region that is not common across the data set,
Right.
but we can capture it specifically for that shape. Okay. Great. Recent works have circumvented the need for 3D data by proposing text-driven segmentation of 3D shapes. And while text, as we said, can be specific about the work, it struggles about where. Take for instance, this example, where we use the text wheel in order to segment the wheel region of this card. But as you can see, this method selects all the wheels. But if we want a specific wheel, it is hard to get it with text. But in our case, we are click-based, so we can click on the wheel that we want in order to segment the specific wheel, the specific region that we want to work with. So we said that we do not have a 3D data set for interactive segmentation of 3D shapes, but luckily we have an interactive 2D model for segmenting images. So we can click on an image to segment the region corresponding to our clicks, positive or negative. But note that, so we want to use this 2D model, this is the segment anything model. We want to use it for interactive segmentation in 3D. But note that this is a 2D model, and there are significant challenges for using a 2D model for segmenting in 3D. To start with, there is the consistency challenge where 2D segmentation masks are highly inconsistent across views. Let's say that we take this 3D shape and this click in 3D, and we do project and segment. So we render it into 2D images, feed it through the same model, project the 3D click into 2D, and get the segmentation of the rendered images. And you see that although it's the same shape and the same click in 3D, the segmentation masks differ substantially across views. And what we want is a consistent segmentation where we want to segment the shape in 3D, and no matter which view we take, the segmented region in each view corresponds to the same region in 3D. And this is what I think that.
And the light is fixed in a position when you render.
So yeah, we use the same lighting conditions.
Okay. And the light is on the camera?
So we have a camera, we have a light source, and we render it from different views.
Okay.
So the setting is consistent. The only thing that we change are the views. And you would have expected that you would get I mean, obviously not. Sam,
You get different induced edges when it gets projected to 2D.
right. So this is exactly the challenge that we're facing, because the 2D segmentation model process each of these images separately.
Yeah, I was just confused because the one on the left is lit slightly differently than the one on the right, but that's just because you make the slide.
Yeah.
In a different way.
What do you mean?
The lighting.
The lighting on
Ah,
the far left is different from the bar that's lighting on the far right. The ones on the right are consistent with each other, I think.
uh-huh. Yeah, so they are consistent. Maybe it doesn't translate.
Yeah, maybe it's sort of a normalization or something.
Yeah.
Yeah, great, I understand, thanks.
Okay.
I had two questions. So one thing was, I forgot one of them, but I'll ask the first one. So a few slides ago, you talked about how the previous method would depend on like a labeled data set,
Mhm.
and now you're more general.
Mhm.
But I guess like the caveat is it's still limited by the generalization of the foundation model like SAM, right?
You are totally correct.
The second thing was if you're using untextured meshes, then perhaps a part which is defined because of the texture will not be discovered, or do you use textured?
Exactly. Okay, so these are great questions. Regarding the first question of being limited by the foundation model, which is correct. I totally agree. And every method that uses the 2D foundation model, I call it at the mercy of the 2D foundation model. However, the framework that we're talking about, it's general. So today we have SAM, tomorrow we have SAM2, and we can replace the foundation model with a different foundation model. And as long as we have the click-based interface,
yeah,
we can use it and improve what we can get from the foundation model. Regarding the second question, regarding texturing the shape, what we wanted here is to capture the geometrically related regions of the shape. And if I texture the shape, I might be biased according to the texture. And nowadays there are 3D texturing models, and they have their own biases.
Yeah.
Okay, so if we use textured shapes, we would be influenced by their texture. And let's say that I want to capture the geometry, the textureless regions of the shape, and this is what we did here.
Yeah.
But of course, you can use texture, and it would be interesting because I guess the texture can help the segmentation, but at the same time, we need to consider how to avoid these biases within the texture.
Yeah. And I guess another question was about SAM's performance on untextured meshes versus like more realistic renders.
Yes.
Yeah.
So it turns out that SAM
Works well for this.
is able to work on rendered untextured shapes.
Yeah.
But it's an interesting question to see how it would operate on textured shapes and how to counteract the biases of the texture.
Yeah. Okay. Thanks.
Great. Another major challenge with using 2D models for 3D segmentation is the occlusion challenge. So let's say I click on the back part of this back region of that part. So a 2D segmentation model would segment the region of that part where the click is visible. However, we are interested in 3D segmentation, 3D meaningful segmentation, meaning we want to segment also this region of the part. But with a 2D model, we can't, because the click is not visible from this angle. So we cannot segment this entire 3D part with a 2D model. Another challenging setting is if we want to segment the shape with two clicks occluded from each other. So we have a click on the back and a click on the front, and these clicks are occluded from each other and cannot be seen together from any single 2D view. So we cannot use this setting with a 2D model. Okay, so what did we do? We designed an interactive segmentation method that operates entirely in 3D. What our method gets is the 3D shape. It first takes the coordinates, the vertex coordinates of the shape, and maps them with an encoder into deep features, which are SEM-like features. How could we distill the encoder of SEM such that we encode each vertex into the deep features which correlate to the SEM features. Then we take the clicks of the user, which can be positive or negative, meaning we want to include or exclude a region, and we feed them through to our decoder. And our decoder contains our novel interactive attention mechanism that interacts the vertex features with the features of the click points to produce the updated click features, the features that are for each vertex that are updated according to the clicks. We take the a priori vertex features, which are dependent on clicks. So we have both the information of before the clicks, like the intrinsic, let's say, information, and the updated information. We map them through an MLP to the probability per vertex in 3D of belonging to the region corresponding to the clicks. But as we said, we did not have supervision for this process. We do not know how we should predict this probability. So what we did, we used rendering, we rendered our probability map over a probability field over the shape into 2D images. And then for supervision, we rendered the shape and projected the clicks in 2D, fed them through the 2D foundation model for segmentation, SEM in this case, and got segmentation masks for supervision. And as we've talked before, okay, and then we applied binary cross entropy to compare our prediction with segmentation supervision from the different views. And as we discussed before, the segmentation regions in 2D are highly inconsistent, but in contrast, our segmentations are 3D consistent by construction because we predict the segmentation directly in 3D. And as you can see, ISEG managed to learn a coherent segmentation function out of this highly inconsistent 2D supervision. Yeah.
So could I consider it as a kind of clever voting scheme in 3D?
You might say, so the way so it's, let's say, an implicit voting, because we use these features and MLP that combines the information from the 2D views. So I'm thinking about it like, let's say, a signal to noise problem where there is an underlying segmentation function that we want to reveal, that maps from the clicks into the per vertex probability, and we have very noisy supervision, but we managed to, you see, the segmentation region is shared across these views, and we managed to reveal it out of the noisy segmentation maps.
Like, may I add to that? It seems like the optimal probability then would be like the average across all views at that point, right? That would be like the best it can do for like a point.
Why I mentioned voting, because voting is not
exactly.
average. It's a mode.
Exactly.
It's like
Yeah.
finding.
Yeah.
The modes, modes is right perspective. Yeah, I think it feels right, because it feels We also call it modes. Not sure we called it in the paper like this, but yeah, it captures the modes of the segmentation of this chip and then the clicks.
And so all the examples I'm seeing here, I assume this is true across all these training examples, is all of the clicks are visible from the same view because you have to have that in order to supervise with SAM. But you're just sort of crossing your fingers and hoping that because you learn this model to operate in 3D, that it will then generalize at inference time to clicks that are not necessarily mutually visible from the same view.
Yeah, so we hope for that. I mean, we worked in order to make it happen. So
Yeah.
but it's a bit technical details. It's a bit in the weeds, but nonetheless, what we did here, we trained the encoder and decoder separately. Okay, so the features that we get for the vertices describe some property, some semantic segmentation oriented property of the clicks. So when we segment in 3D, if we, let's say, do this, apply this click on the other side of the horse face, where it is occluded from the first click, since we distill the SAM-like features on the shape, we have the similar semantic meaning of the horse face, whether it's here or here.
Gotcha.
And it works.
Yeah.
Okay.
Makes sense.
Oh,
But actually, you don't necessarily care that you have the same semantic feature. You just care that it produces the same segmentation.
yeah, exactly. But I'm basing my the interaction between the clicks and the rest of the features, but according to these features. So they need to have some information that enables me to project them to the positive and negative clicks and their interaction. So
Yeah. But I think it's a positive, actually. But I think it's a positive because we know that these features aren't 3D consistent.
they are.
And so when you aggregate them, you actually ruin your model performance because you're averaging things that are sort of distant in the latent space, and you end up somewhere in the middle that does not give you good segmentation. But you avoid that problem with this formulation.
Yeah. So just so I understand correctly, it seems like you pre-train the encoder such that these features are sort of supervised using SAM features from different views,
Exactly.
and then you freeze it. Did you experiment with not doing that? Just training the entire thing end to end where the only supervision comes from
Yes.
these? Yeah.
Definitely, we did it.
Yeah.
And it didn't work. I mean, it worked well for the training vertices.
Mhm.
I didn't mention it. We trained this model with a subset of the vertices, and this is an optimization problem. Okay, we optimize the encoder and decoder for per shape.
Yeah.
Okay, and we use a subset of the vertices, small subset of 3% of the vertices that are possible to be used as clicks. Okay. But it generalizes to clicks that we've not used. Okay.
Yeah. Cool.
So it generalizes in several axes, in the vertex axis, in the view occlusion axis, in the number of click axis.
Nice.
Okay. Yeah. Okay. Yeah. Go ahead.
Good question. I might be getting ahead, but in the end, you need to produce specific segmentation with some threshold, right?
Right.
How should the threshold?
Okay, that's a great question. So what we've noticed that we have populations of these probabilities. So if we divide, so if we plot the probability per vertex, you see the population of low probability and the population of high probability. And in order to get sharp segmentations, we use also threshold. The simplest, so the idea here was to show what the model can give. And of course, you can do post-processing, you can do thresholding, you can do graph cuts, you can do many things. But in our case, we saw that also thresholding is enough to convert the soft segmentation prediction into hard segmentation. Yeah,
I think we can, well,
Okay.
lastly, yeah.
yeah.
I don't wanna delay you. Very fun stuff.
Okay, but it wasn't enough. We had to deal with another challenge, and it was the click configuration challenge. As you can see, there can be different click configurations. There can be a single positive click. There can be another positive click. There can be another negative click, and there can be a combination of the two click types. And we could have trained a different ISIC model for each click configuration, but it is infeasible because we do not know in advance which click configuration would be used. So we asked ourselves, how can we train a single model that supports different number and type of clicks? And the answer was our interactive attention mechanism that, and let's see how it works. And this is one of our technical contributions in this work. The interactive attention mechanism gets the vertex feature, the encoded features per vertex, and the click features by the user, which can be positive and negative. And then what it does, it learns the representation of what it means to be a positive click and a negative click by projecting the click features into keys and values for a positive click and negative click, and also it's projected into a value for positive and negative, and we learn different matrices to learn the representation of positive and negative clicks. Then we project the vertex features into queries that are interacting with the keys of the clicks, like in the attention mechanism. We get attention scores that are multiplied by the values of the clicks, and we get the updated vertex features of per vertex. Now, this mechanism is interactive in the sense that if we add another click, a positive click in this case, what it will give us, it will give us another key value, which will be correlated and give us another attention score, which will be multiplied by another value, and will end up with the same feature size for that click. So this attention mechanism extends the dot product attention mechanism, and it learns different representation for positive and negative clicks. And as you can see, it can support different number and types of clicks, and it enable us to train a model that supports different click configuration, a single model. Okay. ISIC produces fine-grained customized segmentation for the shape at hand. As you can see, we can get the bulb of the shape. And an anecdote, when I showed it to Rana, she said, I've been working with this lamp for many years, and I didn't notice that there is a bulb here. But we can click on the bulb and get it. And we can also add another positive click to get the region around it, and we can also get the upper region of the shape and exclude this part of the shape. And these regions are hard to get back with text because this shape is symmetric. Also, it's hard to describe them, but it is symmetric. So which shape or lamp would be segment with text, but here we can click on the region that we want in order to segment. Okay. And coming back to the occlusion challenge, here with ISIC, if we click on the backside of the backpress, the front side is segmented as well. And if we add another click included from the first, the entire part of the chair is segmented, and this is what we want. So ISIC managed to generalize far beyond its training data because these cases do not even exist in its training data, and still it manages to produce meaningful 3D, meaningful regions in 3D. Yeah.
I'm wondering about how much, to what extent, if you want this to generalize to arbitrary categories of shapes,
Mhm.
To what extent does it generalize beyond the categories it's trained on? So like, is it important to train when you come up with these sort of, SAM generated training examples to really cast a wide net across many, many types of shapes? Or is this thing learning like a low enough level operation that I can train it on, say, chairs and tables and airplanes and find that it segments horses just fine, right?
That's a great question, and
Yeah.
this is the follow-up work that we're working on. And in this work, we optimize the ISIG model for a single shape, but this architecture can be applied
Ah, I see. Got it.
to it's the same thing. I can extract some features or whatever
Right.
the new segmentation model and apply the decoder that is learned across several shapes,
Okay.
not a single one. Okay, so what we've seen so far that it can generalize to different instances of the categories that it was trained on, and it can generalize to some extent to categories that it hasn't seen. So, but there's still work. Okay. And here it's in grade, yeah. Okay. Let's go.
Yeah, sorry, last two questions.
Yeah, okay, yeah. Anyway, let's summarize this part. In this work, we've suggested an interactive 3D segmentation model that produces segmentations in customized segmentation based on clicks. These segmentations are 3D consistent by construction. They are happening in 3D and they are learned from highly inconsistent 2D masks. And it handles occluded regions and click, which do not exist in the 2D training data. And this method contains the interactive attention mechanism that supports different number and types of clicks and enable us to train a single model that supports the different click configurations. Yeah. Okay, yeah.
I'm wondering the click-based technique because why not using the lasso tools? I mean, you can directly draw a region of the interest. It seems to be more explicit to represent where you want to include in your segmentation.
I agree that that's a trade-off between ease of use, as I see, ease of use and precise of result. You can draw regions. You can even do it with sand, draw rectangles over the image. But I find it that clicking on the region that I want and the model understands what I want is easier than dragging, because you need to be more careful where you draw your rectangle and the size and the position. And here you can click. And another thing that I haven't talked about is that this model is very robust. I can click on different regions and the result is stable. So I don't need to be that precise with my click. So it is very easy. Okay, cool. Let's move on. Let's move on to talk about the second section of the talk, which is local editing, local texturing of 3D shapes, and it relates to work that we published at the last CVPR conference. Okay, what our vision? We are given a 3D shape and a text prompt that describes an edit. And what we want to do, we want to edit the texture of the shape locally. So it means that we want to change only the region related to the target edit and keep everything else the same. Here you can see that we want to add a gold chain necklace to the discount model, and you can see that the gold chain necklace is added, and everything, all the rest of the shape is untextured. Just we add the texture of the targeted.
It's not a geometry change.
What? No, yeah, exactly. It's not a geometric change. Exactly. Here we focused on textures. We have other words on geometry that I mentioned later, hopefully. Okay, but why is local editing is an important problem? Why do we even care? It turns out that users oftentimes want to change specific aspects of their 3D of their asset while keeping its identity the same. So in this example, we want to add a blue apron to this teddy bear, but we don't want to add it to any teddy bear, but rather this specific teddy bear. So we want the edit to be local. We want to change only the region relate to the apron and keep what makes you yourself, keep the identity of the teddy bear the same. Okay. What does many 3D editing works do? They do global 3D editing. For example, here we can see text to mesh that creates texture and geometry for the entire shape. And there is also a work that creates the texture of the shape for the entire shape. And although these textures are very impressive and detailed, they do not support the local edit property that we are interested in. But in our case, the edit is localized, and it is confined to a specific region related to the text font. And here you can see several examples. We can add the gold chain necklace that we've seen before, and we can add the turtle shell to this GAN model and many other examples. But this local texturing problem is very challenging, and for several reasons. To start with, we want to ensure that the edit happens at the desired region and only there. So in our case, we add localization. We'll talk about it in a few slides. We also want to make sure that the texture matches the local region. And here you can see an example where the localization and texture doesn't match each other, and we get artifacts in the texture. And another thing in specific and special to our case is that the edit happens usually in small regions of the mesh. So we want high enough resolution in order to get a highly detailed and expressive texture. Okay, and here I can see an example of the low resolution supervision and what happens with our higher resolution supervision. So let's see how standard 3D texturing pipeline works. We have a 3D shape. Also in our case, we take the coordinate of the shape and we feed it through some neural network that predicts the texture over the shape condition on a text font. In this case, a gray cow with a colorful crochet. And the question is this pipeline enough for local texture? It's not. Okay, and why it's insufficient? Because we do not have localization. And for example, if we want to, and since we do not have localization, the entire shape gets edited, and we do not have control over it. Okay, let's say that we want to add a gray polo shirt to this human figure. So we get the sort of a gray shirt, but we also get a lot of things that we do not want. We get sort of pants and color scheme and facial attributes, but we are only interested in the shirt. So what we did, we added an explicit localization over the shape in 3D. So what we did, we instead of a neural network for texture, we had a neural network that predicts the localization. The probability seems similar to Isaac. It predicts the probability of over the mesh for a region corresponding to the text from describing the edit. Okay, but different from Isaac here, we supervise with a visual model, with a diffusion model, and we need some visual property of the mesh in order to supervise this branch. So what we did, we converted the probability prediction with a color blending. So we multiplied the probability by the yellow color and 1 minus probability with gray color, and in order to get a visual property over the mesh. And now we describe the localization with the text font. So we use the gray cow with the yellow head. And since these models are good at stylization, the shape, the only way that we'll have a gray cow with the yellow head is if the probability corresponds to the correct region of the edit. Okay, so we found a way to translate the probability property into a visual property and supervised by the diffusion model, by the visual model. And now, in addition to the texture branch, we have the localization branch that explicitly masks the texture branch to get a localized edit. And coming back to the gray polo shirt, when we add localization, we get only the gray polo shirt region as we wanted. And even more than that, you can see that now the gray shirt is much more detailed because this part of the model is focused on getting the best local edits of the shirt that it can. Okay. Another important aspect of our method is that the localization and texture are optimized together. Here you can see what happens if they do not. If we optimize them independently, there is a mismatch because there can be many possibilities of placing pink sunglasses on this octopus model. And if we optimize them in series, first the localization, freeze it, and then the texture, then we get an inferior solution because the localization and texture do not inform each other. And if we optimize them together, they mutually benefit each other, and we get much better localization and more detailed segmentation textures. Okay, we've talked about how our pipeline works, and we said that we want to supervise it with a 2D model, but we didn't say how. So how this current methods use a 2D model. They usually use a diffusion model that takes an image and a text prompt and does a process that is called score distillation sampling. And I guess score distillation sampling is known, so I will skip it. Okay. Great. So basically, score distillation sampling tries to capture information from the diffusion model and aligns the edit that we want according to the prior of the model. But the problem is with standard SDS is that it is low resolution. Here you can see an example of a generated image by diffusion model according to the text prompt and iris shutter. And as you can see, this is the resolution usually used for score distillation sampling, and this is low resolution. Okay, but it is not good enough for us because we want to do the edits at the local small region and we need high resolution. Okay. And we asked, how can we increase the supervision resolution? It turns out that there are cascaded diffusion models that can produce, we know that they can produce high resolution images. And one way to do that is use a cascaded model that includes several stages with increasing resolution, where each model takes the previous output of the previous model and as an input and increases the resolution. So we get a high resolution detailed image. And the question is, how can we use them for supervision? It turns out that standard SDS was used in such cascaded model, but only using the first stage of the model. But it feels like we're leaving a lot on the table because we have these stages trained already. So why not use them for supervision? Okay, and this is what we did in this work. We proposed a cascaded score distillation, which distilled information from several stages of the diffusion model and get high resolution supervision from the high resolution stages as well. Okay, how does it work? We take the shape and render it into different 2D images, different resolutions that matches the resolution of the cascaded model. And similar to the score distillation process, we add noise to these renders and feed them through the different stages of the diffusion model in order to get the supervision that we want, but different from this. So this is the standard SDS, but different from SDS, we also use the high resolution stages and we also feed them the lower resolution of the previous stage. So we mimic the way these diffusion models were trained, and we can get high resolution supervision. So we predict the noise and compare it to the edit noise, and we get more information from this existing diffusion model, which is very exciting. And how does each stage influences the result? Here is the supervision only with the first stage of the diffusion model. We use deep fluid IF. This is the supervision with only the second stage. So, okay. So as you can see, we see interesting things here. As you can see, the first stage has global understanding. It knows where to put this fancy gold watch on the wrist, but
Oh,
but
see what you mean, sorry, yeah.
cool. But the details are the quality of the texture is low. The watch is blurry and we do not have details. On the other hand, the second stage, it gives us high resolution texture. You can see the hand of the watch, but it doesn't have global understanding. It puts it near the finger, but rather on the wrist. And if we combine the supervision from both stages, we enjoy the benefits of both worlds, and we get the watch at the right location with highly detailed texture. Okay. 3D paintbrush produces high resolution textures for diverse edits and different shapes. Here are two examples. There are many more in the paper. Here we can see that we added Barcelona jersey shirt to a Lego minifigure, and you can see that we managed to get the emblem of the shirt, which is very small and intricate, and it is very similar to the actual emblem of the jersey group. And here it's hard to see in the monitor. We managed to get wrinkling effects in the cape of the superhero dog, which are details that we wouldn't have get if we would have used standard SDS. Okay, and here we can see a quick comparison between SDS and CSD, and as you can see, for the colorful crochet shell, rather than a blurred texture, we get the crochet pattern on the texture, and here for the tiger stripes shirt on this robot figure, instead of blurry stripe pattern, the stripes pattern are much sharper with CSD. And this is very exciting to me, the CSD mechanism, because it's general purpose. It can be used with different 3D representation with Gaussian flats or implicit representation with different diffusion modes and maybe for different tasks. So we managed to take existing diffusion models and extract more supervision, higher quality supervision out of them. And it can be used. Actually, we have used it for other tasks and it worked amazingly well. Okay, to summarize. In this work, we proposed a 3D paintbrush, which is a method for text-driven local 3D editing of 3D shapes, and it produces localized texture localization and textures on 3D shapes. It corresponds to prescribed text. We do the optimization of localization and texture jointly, so they mutually benefit each other, and we can get higher quality localizations and texture that conforms to them. We propose the new cascaded score distillation loss, which exploits diffusion model higher resolution stages of diffusion model and enables us to get small, highly detailed textures. And these textures were optimized using a 2D model. So we give it a text prompt and it finds both the local region and produces the texture without using any 3D data. Okay. What's next? What other things we can do with intuitive interfaces and have to get cool applications for 3D? In 3D Paintbrush, we've talked about creating a local edit using a text mode. Here you can see that I wanted to get a floral Hawaiian shirt. But what if I have my specific beloved Hawaiian shirt that I want to edit the shape accordingly, and it is very hard to describe with text. So what we've been working on is image guided local editing, where we use the image to guide the local editing of the 3D shape. And now we can get the flower and leaf pattern that is similar to the pattern that appears in the image, and we have much more control over our edit. So instead of using 1,000 words, we use an image and got our edit. Okay. What other properties we can influence with intuitive interfaces of the 3D shape? In this talk, we've talked about localization and texturing of 3D shapes, but another important aspect of 3D geometry is the geometry itself. And in this year, we have two works on this subject, where this work mashup was presented at the last 3DB. And what it does is text-driven deformation of 3D shape, where we can specify multiple concepts and deform the shape towards these concepts and their blend, and we can control the location that they manifest. And the concepts can be prescribed with text or images or even different shapes. And I'm very honored to share that it happened last week that this work was acknowledged with the best paper honorable mention at 3DP. So we're very happy about that. And another upcoming work is Geometry in Style, where we take a 3D shape and use a text prompt to stylize the 3D shape. So in this case, we want to keep the identity of the shape, in this case a vase, and apply to the theme, the style that we describe with text. And here we make a vase that is pineapple theme. It looks like a vase, but it looks like a pineapple, but still you can recognize that it is the vase that we started with. Okay. What about the future of local editing with 3D shapes? So I think we will be asking ourselves interesting questions like, what other properties, what additional properties we can influence of the 3D shape with simple and intuitive interfaces? In this talk, we've considered static 3D shapes, but what if we consider the dynamics of 3D shape, like motion and articulation? And what other tasks can we, tasks can we perform? So let's say if we consider the time axis, maybe we can do tasks like text-driven animation, where this creating animation is very, very challenging with common tools. And to me, the $1 million question is, how can we have more control over our edits? So if we do an edit manually, we have full control over the edit. I know exactly what I want to do, but it is very tedious and hard. On the other hand, the AI-based models, it is much easier, but it may not be exactly what I had in mind. So how can we increase the control? And a straightforward possible follow-up work based on the works that we've seen is localized text-based editing. So I can use text to describe the edit that I want to make, what I want to do, and I can use a click to determine where I want it to take place. Anyway, I think the future is going to be very interesting, and I'm very excited about the challenges that lie ahead. I want to thank my collaborators on the ISIC and 3D Paintbrush, Faye, Dale, Sudarshan, Fear, and Rana. And I want to thank you for listening and asking this interesting question.
Right. We're slightly over time, so see you all next week.
Thanks, everyone.